Moving on to our AP style questions. So we start with this first one where we have two questions related to this graph over here of a cart moving along a straight line. So the first question asks, what is the magnitude, we want to rank based on the intervals given, the magnitude of the average acceleration of the cart. We know that for a velocity versus time graph, acceleration is the slope, so that's going to be what we're looking at. I'm going to go ahead and actually calculate the slope for each one of these segments. So for B to C, and I'm skipping to the easy one first, my slope is 0. I'm going to zoom in here a little bit, and I'm going to move on to the slope from C to D. So if we look at this point here, we have the point 1, 8, and at D we have the point 1.4, 0, because each one of these blocks is 0.2. So I find that my slope here is negative 20 meters per second squared. From D to E, E is at a point of 2, negative 4. So I find that my slope here from D to E is negative 6.67 meters per second squared. So now I have three of my slopes here, from D to E, from C to D, and from B to C. The only thing remaining is this final slope from A to B. This one's a little bit tricky though because it's a curved line, but it did mention we want the average acceleration. So all we're going to do is find the slope of the line directly connecting A to B. So going from 0, 0 to this point here, which is going to be 0.6, 8. So I get a slope of 13.3 meters per second squared. So now it's just a matter here of ranking them. I see that C to D is the first one, so that eliminates these two choices. After that, it's going to be A to B, followed by D to E, so that eliminates choice A, and then finally B to C, which is 0. Keep in mind that the negatives don't matter because of this word here, magnitude. We only care about the number. Moving on to question 7 here, we want to know for which segment does the object move the greatest distance. So for this one, I am thinking about area. And so I'm going to go ahead and split these segments into area. So I can clearly see that C is not the biggest. So that one, C to D here, is not the biggest. So that one's out. And this D to E area is also, if I look at it, it's a triangle that is clearly smaller than B to C. So that one is also out. Now I could go ahead and actually calculate these, but we can do this visually. To compare B to C to A to B, what I'm going to look at is this rectangle here is the same as B to C. And so now I realize that in going along this line from A to B, we don't get that full rectangle. There really is only just this little piece of the rectangle missing. So this section right here is almost as much area, meaning almost as much distance as B to C. However, with A to B, I also get this segment in here. And that, combined with that rectangle, is going to give me more area than B to C. So my answer here is going to be A to B. If you wanted to actually calculate it, you could try and calculate that area. For A to B, it's going to be a little bit tricky because of the curve, but what you could do is simply try and approximate it as a bunch of triangles and rectangles and get something close to the curve, and I think you're still going to find that it's a bigger area than B to C and certainly a bigger area than C to D and D to E. Alright, moving on to question 8 here, we have another graph. Now this is one that you're going to see throughout the year, throughout the AP exam, and this is one where we have to select two correct answers. That's something that's a little bit different than ones we've done thus far. So we're going to have to go ahead and pick not just one correct answer, but actually two correct possible answers here. So let's go through them one at a time. So which of the following statements are correct based off the graph shown to the right? So the first is the object is speeding up from 7 to 9 seconds. Well, if I look here from 7 seconds to 9 seconds, that's that region right there. And that is true because we're getting further away from the x-axis. So that represents speeding up. So that statement is true. Let's move on to the next one. The object is slowing down from 5 seconds to 7 seconds. Well, that would be this region right in here. And what I see is a horizontal line on my velocity graph, which means that during that segment, 0 to 5 seconds, I have 0 acceleration and I'm traveling with constant velocity. So that one is no good. That one is not correct. For C, the magnitude of the acceleration from 2 to 3 seconds and 4 to 5 seconds is the same. So I look here, I have 2 to 3 is this region right here. 4 to 5 is that region right there. I can see that the slope is the same, and that's what we're looking at when we talk about acceleration. So same slope, so that one is correct. Might as well check part D just to make sure. So part D says the object has a negative acceleration from 9 to 10 seconds. Well, acceleration is my slope. That is a positive slope, so a positive acceleration, which means that that one is not correct. So my final answers are both A and C. Moving on to some of our free response problems, we have another quantitative translation problem here about a car that's initially at rest on a road and a truck that drives past it. We're told that as soon as the truck passes the car, so at this point right here, the truck begins slowing down. The car, on the other hand, begins speeding up, but it only has 3/4 of the acceleration, 3/4 of the magnitude of the acceleration. So the first thing we want to do is on the axis below, we want to draw the velocity versus time graph for both objects. So I'm going to start with the truck here, okay, and I'm going to have its velocity versus time graph start right here at a point that we're going to call VI, the initial velocity of the truck. I know that that truck is going to be slowing down, so we're going to have a downward sloping line until it reaches until a time of TF. So I'm going to use a good amount of the graph, and I'll just say this point right here is TF, and we do want to label these points. And now I'm just going to draw that graph going from here down to TF, something like that. Okay. For the car, I'll draw that in a different color. So let's say this is the truck actually. For the car, we'll draw it in black, and we're going to show that car speeding up. And so the one thing that I do want to keep in mind is it's speeding up at a rate of 3/4 A. So it's not speeding up at the same rate. It should not have, if we're being really technical here, the same slope. So what I would do is I would think about this. The truck loses, and I did this on purpose, 1, 2, 3, 4 blocks along the graph in that time. So I'm going to say that the car gains 3/4 of that, or 3 blocks. So the car is going to start from rest here, and it's going to speed up, but it's not going to reach quite the same speed. Now, this was an actual exam. It kind of depends on what the wording was, whether or not they'd nitpick about this. But we should definitely show that the final speed of the car is less than the initial speed of the truck, because the truck's acceleration is A, whereas the car's is only 3/4 A, not as much. Moving on to part B, when the truck finally comes to a stop, will the car be in front of it, behind it, or even with it? And we want to justify based on our graph. So here's what I would think about right off the bat. The distance the truck travels and the distance the car travels, those are simply the area under the curve. And if I look at the area under the curve for the car, and I look at the area under the curve for the truck, I can clearly see, and I don't even need to sketch this out or do the math, I can clearly see that the truck has a greater area. So that answers our question. So we're going to say that the car will be behind the truck. And the reasoning, justifying it with the graph above, is that the area under the curve for the truck is greater than the car. The last thing I would add here is simply that this means the displacement of the truck is greater than the car. Okay, just connecting it back to the motion itself. Moving on to part C, we want to derive an expression for the time it takes a truck to come to a stop in terms of VI and A. There's a few ways of doing this. We could jump to our acceleration formula. That is one way. What I'm actually going to do though is I'm going to use my graph, and I'm going to use the fact that slope equals my acceleration, which is equal to change in y over change in x. So I'm going to go ahead and use information I know about the truck. I know that for the truck it starts up here at this point 0, vi. I know that it ends here, reaches that final time at the point tf, 0. I also know that my acceleration here is negative a. The magnitude is a, as it was stated earlier, and it's negative because we're traveling in the positive direction but slowing down. So what I'm going to do is I'm going to say that negative a, that slope, that acceleration, is equal to my change in y, so 0 minus vi, over my change in x, tf minus 0. So I get that negative a equals negative vi over tf. Okay, I can go ahead and cross multiply here, and I find that negative a tf equals vi. So that means that tf is equal to vi over a. One important thing to note is that we asked for the final expression in terms of vi and a, and I was able to make sure that it was in terms of vi and a. So you should always do that final check to make sure you have it in the correct terms based off of the problem. Moving on to D, we now want to find the displacement, so we're instantly thinking about the area. So thinking about this triangle here for my truck, because it's the displacement of the truck, that's going to be equal to 1/2 base times height, 1/2 TF, which is my base, times my height VI. But I notice my final expression needs to be in terms of VI and V and A, so that TF is out. Luckily, though, I just found an expression for my final time, and that was VI over A times VI. So what I end up getting here is VI squared over 2A. You also could say 1/2 VI squared over A. There's lots of possibilities, but that to me is the simplest form, although I'll accept others. And the last thing is derive an expression for the displacement of the car in terms of VI and A. Well, once again, we're looking for our area here, which is 1/2 base times height. So 1/2 TF. Right, now I'm thinking about the triangle, though, of the car. Okay, and so the height is no longer VI because the car does not get all the way up here. What I do know, though, is my acceleration is 3/4 as much, which means my final velocity will be 3/4 as much. So I can say that my height will be 3/4 VI. Once again, I'm going to plug in that expression I have for the final time, which is VI over A, multiplied by that velocity, that height, which is 3/4 VI. And then I can go ahead here and solve, and I end up getting on top 3VI squared over 8A, or 3/8 times VI squared over A. Moving on to our last problem here, we have a situation with Chuck who's playing soccer, and we're told that he uniformly accelerates from rest to a velocity of v with an acceleration that has a magnitude of a while running down the field. So let's break down that first part. He's accelerating from rest to a velocity of v. So in my velocity versus time graph, I'm going to say that this point here is v, and I'm accelerating from rest to that point. So something like this. Okay. On the position versus time graph, accelerating from rest, we start with a horizontal line, and we're going to be concave up because we're speeding up, accelerating from rest. After reaching this velocity of v here, okay, he realizes that he's running the wrong way, so he slows down to a stop with an acceleration of 1.5a. So we know that we're going to slow down to a stop more quickly. Okay, it's actually going to take 2/3 as much time because the acceleration is 1.5 times as much. All right, although we don't necessarily need to draw this perfectly to scale, I am going to put that in there, and I am going to draw it to scale. It took 3 blocks, whatever their units are, to speed up to that speed of v. It's only going to take 2, or 2/3 as much, to slow down. On my position graph, what's going to happen if I'm slowing down is I'm going to level off and become concave down while continuing to have a positive velocity causing me to slow down. And we see that in the graph as the graph is flattening out. The only real quantity I think we can label here is this v for that max velocity. The rest of it, I don't know how much we could actually label. We don't really know much about the time. And with curves, it's tough to be able to label the acceleration of the velocity, so we're not going to worry about that. So my first question asked me to derive an expression for t1, the time it takes Chuck to reach a speed of v while speeding up. So once again, I'm going to use the fact that slope is equal to my acceleration. So thinking about this velocity versus time graph, I'm starting at 0, 0, and I know that I reach a speed here of v in a time of t1, the time for me to speed up. So I'm going to say that my acceleration, which is a, is equal to my change in y, v minus 0, or my change in x, which is t1 minus 0. And so I end up getting here acceleration is v over t, 1. And when I solve for t1, I find that t1 is simply v over a. For part C here, I now have a second part of the graph that I want to analyze. I want to look at this portion where the object is slowing down. And we want to know the time it takes for that to happen. So, just real quick as this note here, it tells us that T2 is simply the difference in time here, the time it takes only to slow down, which means that that final point when we come to a stop here, and I realize that's not drawn to scale, is actually going to be T1 plus T2, comma 0. Okay, because T1 plus T2 is going to be the total time when we're at this point here. So I'm once again going to start with this idea that slope equals our acceleration equals delta y over delta x. Give myself a little more space here, and so what I get is acceleration is negative 1.5a. We were told that in the problem. And my change in y is going to be 0 minus v. And my change in x is going to be that final time, t1 plus t2 minus my initial time, which is t1. T1's subtract out, and so what I'm left with is negative 1.5a equals negative v over t2, which means that t2 equals v over 1.5a, or I could also write this here as 2v over 3a, or 2/3 va. Alright, I'm going to bring my graph back for this last part here, for part D. I'm going to derive an expression for the total displacement of Chuck in terms of v and a. Keep in mind what I just discovered here. This time here is t1, but my total time is actually going from the very beginning to the very end, t1 plus t2, because I know that this interval here is t2, much like this interval was t1. So I want to find the total displacement. I know that my displacement is equal to my area, so I'm simply finding the area of that triangle there, 1/2 base, which is t1 plus t2, times my height, which is v. Keeping in mind once again that I need to answer this in terms of v and a, I'm going to make some substitutions because I just solved for, and this is another common thing you'll see, in the previous part I just solved for t1 and t2. A lot of times the AP exam likes to pull parts of earlier problems to answer a final problem. So, substituting in for t1 here, I have v over a plus t2, which was 2v over 3a. What I'm going to do is I'm going to find a least common denominator, which means multiplying this one, top and bottom, by 3. And so I get 3v over 3a plus 2v over 3a all times v. I combine these fractions and add in the 1/2, so I have 1/2 times 5v over 3a times v, which is really just v over 1 at the end there. When I multiply all that out, I'm going to get that my displacement is equal to 5v squared over 6a.